Let us now describe the basic elements of a quantum network. We have the physical medium that enables the transmission of quantum information, that is, the quantum channel. We have the device that allows to extend the reach of direct connection links, that is, the quantum repeater. And finally, we have the device in charge of performing the quantum information processing for the user. We call it the end node or quantum node. The role of the channel is to transmit quantum information between adjacent nodes, be it end nodes or quantum repeaters. Although there are some intriguing alternatives like cargo ships that have been proposed, in practice two types of channels are used: free space channels and fiber optical channels. Free space channels have smaller losses but are normally restricted to line-of-sight scenarios and can be severely affected by daylight. Fiber optical channels have high losses. Transmissivity, as we've already said, scales exponentially with distance, but they have the huge advantage that they are already deployed. Quantum information can be transmitted over the very same fiber optical channels used by the telecom companies. The quantum internet might very well use both types of channels for different situations. In any case, physical channels always introduce a certain amount of loss and noise. The former mostly affects the rate at which protocols can be performed. The latter needs to be overcome either via error correction or via entanglement distillation. Both impose additional requirements on the quantum information processing capabilities of the nodes. That is, the necessary quality of the quantum memory and gates at the end nodes depend on the noise in the channel. Quantum repeaters are necessary both for ground as for satellite communications. Notably, in ground communications, the transmissivity of fiber optical channels scales exponentially with distance, and without quantum repeaters, endpoints in the network cannot exchange quantum information. In consequence, there is no truly quantum protocol that can be performed. The partial exception is quantum key distribution, if one is willing to trust all intermediate nodes. One might naively expect the repeaters to be a simple device that boosts power or amplifies the signal. However, quantum information cannot be copied or naively amplified. Hence, quantum repeaters rely on different paradigm than their classical analogs. The quantum internet of the future will have a full-fledged quantum computer sitting at each node. And indeed, we already know of applications that benefit from these extreme resources. However, most applications of the quantum internet do not require a quantum computer at each node. In fact, many applications require resources as simple as the capability to prepare a small number of single qubit states and the ability to measure in two different bases. Errors in preparation, noise in the channel, all are dealt without quantum error correction but by purely classical post-processing. This means that, at least for these applications, the threshold fidelities and coherencies required are much lower than those necessary for performing interesting computations with a quantum computer. The reason why quantum internet protocols can outperform classical communication with such relatively modest resources is due to the fact that their advantages rely solely on inherently quantum properties, such as quantum entanglement, which can be exploited already with very few qubits. It is fundamentally impossible to replicate the properties of entanglement using classical communication. In contrast, a quantum computer must feature more qubits than can be simulated on a classical computer in order to offer an advantage.